Hello there, CodeMaker4 here. There's just a few things I quickly need to explain about the SMPU that I kind of totally forgot about. So first thing on my list is the logic interface. So if you want to make something for yourself on the SMPU, there is a blueprint, which is literally just the other side of the interface, but just the logic gates and this switchboard, which you can use to set which address range is for whatever component you're building. The interface is quite simple. Here, the SMPU will also be sending out the address it's trying to read or write to, with the lighter color being the least significant bit. The gray stuff is data that the SMPU is getting back from that address, with the white being the least significant bit. And the blue stuff is the data the SMPU is sending to be stored in that address, with the light blue being the least significant bit. Then there's the cyan gates. The left one indicates that the computer would like to read a value from that address. And the middle one is for the SMPU saying that it would want to write a value to that address. And whenever your component is finished with its calculations, it will give a pulse back through the rightmost gate. The timing's just very simple. The moment this gate turns on, it is guaranteed that all of these signals in here are already in the static state that they will be. So all of the data that your component would need, so the address and perhaps the data the SMPU would want to write there, is already there in the same tick that this turns on. And it will stay there until you send a pulse back. And after you send a pulse back and the SMPU is asking to read something, it is expected that you let your data be available for a bit longer at least. Officially, it's until the SMPU gives a new instruction, but in practice, until the SMPU changes the address, it's going to be fine. Just keep your output data there until the SMPU changes the address. You cannot just give the data with a one tick pulse synchronized with that pulse. That won't work. It needs to stay there for a bit longer. Then, pausing and stopping the SMPU. I totally forgot to implement a proper timing mechanism. And if the entire clock sequence is a bit of a hack and a budge. So right here you have two buttons. This button resets the SMPU and then starts it. This button just starts it. Both of which generate one tick pulses. The reset logic is literally these three timers over here. I just gave them a 10 tick delay. You can probably reduce that. This timer here is just to make sure that the reset stuff has finished before it sends the start signal to this OR gate. It just kind of makes the mess. Well, it doesn't improve the mess a lot, to be honest. If you want to pause the computer, the only real way to do that is to kind of disable this AND gate, which prevents the computer from kind of starting a new instruction. So what you do is you turn on this switch to turn off this yellow gate, and the SMPU will stop. It will load in the next instruction, but it will not execute it. You can resume the SMPU from this state. It will kind of try to reread from memory, but it won't increment the program counter twice. So let's kind of see how the instruction loop works. So this component over here is responsible for incrementing the program counter, loading a value from memory containing the next instruction, and then giving a one tick pulse to the decoder to select which instruction to execute. Every time you see this kind of structure of 6 gates, that's a quick component that will kind of keep track of which part of which instruction is currently waiting for memory, such that when this pulse turns on, it knows kind of from where to resume execution again. Because remember, these components can take as much time as they want. So the SMPU needs to account for any random amount of delay you give this. So what happens is each of these timers will make sure there's a bit of delay between every signal. With the exception of these gates, every signal to a component to do something for an instruction is sent via a timer. Reason being, it gives it a purple connection. Again, kind of hoping to make the mess manageable. Didn't really work. So you see all of these 0 tick timers here. Those are just there to make the connection purple. It means that the computer is always at least one tick slower than it could have otherwise been. I don't really care. to be honest. So this here is responsible for incrementing, for going to the next instruction. As you can see, there's 2 OR gates here. This OR gate over here will send a trigger. So all of these cyan gates here are triggers for components to go do something. So it will send a trigger to increment the program counter. And then it will immediately go into that OR gate. And this OR gate will assume the program counter is already in the correct position and read an instruction from there and execute it. So after most instructions, this gate will be turned on to automatically increment to the next instruction and read from it. But after the computer is being resumed or a jump instruction just occurred and the program counter doesn't have to be incremented, this gate will be triggered instead to kind of have it not increment the program counter. So it reads from memory and it does stuff. All of these delays, I measured them, which means that I literally went through every single timer, reduce the timing until something breaks and then increase it again. So this should be all relatively optimized, except for the fact that there's all of these 0-tick timers that are just there for aesthetics. Which of course do have a delay of 1 tick because of how scrap mechanic logic works. Here are the registers. You have A, B, H, L. H and L might be the other way around, I might misremember. There's this empty bit here. This is just a way for the way the SMPU gets data from memory in and out of the main bus that you see over here. There's the counter register with the increment and decrement stuff and some extra logic at top. And there's the instruction register, which remembers which current instruction is being accessed. As said before, you can't arbitrarily load and register from an address. That's not a thing the SMPU can do. Generally, you only have arbitrary access to the A, B, and counter registers, and a bit of access to the high and low byte registers. Every time the computer wants to access a thing to be reading from the bus, it will use this selector over here. So it'll send a 1-tick pulse to the cyan gate that represents the thing it wants to be on the bus. So obviously these things here correlate to the registers. I don't remember what these do. This one here will be for the ALU. Then there's this one, which, aha, no, I remember now. That's for that's how the push, the call instruction works, because that's how it kind of gets the current address. Yeah, it gets an address from the program counter, not from the H and L registers. So as you can see, all of these cyan gates also have a button next to them. So if you want to, for some reason, control the SMPU manually, like pretend you're the instruction decoder, you can. Just make sure no program is running at the moment and use spot guns to hit all of the buttons. They need to be given 1-tick pulses, so a spot gun is the easiest way. There's also a mod where you can hit a gate with a hammer, if you prefer that. That will also give it a 1-tick pulse. As you can see, the bus is over here. It's given extra gates because in practice it will do the exact same thing as an OR gate because only 1 input will be given here. But this is useful if you want to put something specific on the bus, but there's already some other component writing data to the bus. You can use the extra gates to kind of invert bits and stuff. So this kind of makes it possible to write any value to the bus manually if you need to. Of course, do turn these back off if you want to execute an actual program, because it will do funny things if you don't. Then there's the ALU over here. It is a separate blueprint, so if you're interested in that, please leave me a comment. That can be useful for debugging stuff, and if you don't understand the ALU correctly. And I think the only components, there's just a few more things if you want to really dig in deeply into SMPU. Over here you can see the carry flag. Gate is on means carry flag is on. Very simple. Here are the instructions. They are sorted in the same way as in the Excel spreadsheet. So the no op and halt instructions kind of are special and do nothing. And then we start here with ADR, and from that it's obvious. Few exceptions. These instructions over here feature a decoder. That's because they are the ALU instructions and some other more general instructions. that like mostly require the same logic. I don't want to repeat myself 16 times, so this uses a decoder, and it uses some tricks such that, like for example, this one here, you see that not all of the bits of the instruction register are being checked. So it will actually trigger on a range. So specifically, the least given 3 bits don't matter. It will always trigger if the other bits are correct. So this is ALU stuff. And over here we have the various jumps, and like here are the various jumps, and here is stuff that has to do with the stack. That should be everything you need to know about the SMPU if you want to do some more advanced stuff. I'm Codemaker 4. I still don't really have an outro yet, so subscribe, I guess. Yeah, this was running in real time, by the way.